In this video, I will define atomic terms, levels, states, and then determine the lowest energy atomic terms. So first, for a given electron configuration, the combination of a s value and an L value is called a term, written as 2s plus 1 in superscript and the symbol of L here. So when L equals 0, 1, 2, 3, 4, you put S, P, D, F, G here. And this term has a statistical weight, that is the number of possible microstates, equal to 2s plus 1 times 2l plus 1. This is because given the value of s, its z component, m sub s, can be from negative s to positive s. And given the value of L, m sub L, the z component of the orbit angular momentum can be from negative L to positive L. There are 2L plus 1 possible values for m sub L. And then if you also include J, J is a so-called spin orbit quantum number. So what is this? The spin and the orbit angular momentum may be coupled, and then we define this to be J, and it's called a level now, including this S, L, and J. A given level has a statistical weight of 2J plus 1. There's a reason for that. When the spin and orbit are coupled to get this J, again, the Z component of J is M sub J. M sub J may have different values, from negative J to positive J. That's why you have this number of microstates. So finally, if we also include this m sub j, we call this a single state. There are 3 steps to determine the lowest energy terms and then levels. So first, this is the Hund's rule. You always maximize the spin first. And then you maximize L, the orbit angular momentum quantum number. After that, if the electron configuration has a less than half filled orbitals, you minimize J. If the subshell is more than half filled, you maximize J. Again, what is J? The J vector is simply the sum of the L vector and the S vector. And also you can tell that the Z component of J, which is m sub J, equals then m sub L plus m sub S. So now let's look at more concrete examples. Let's look at the D2 electron configuration. First, how do we determine the D2 ground atomic term? So it's very simple. First, m sub L for the d orbital can be from -2 to all the way to +2. And then first, we need to maximize the spin. So what you need to do is you simply fill those orbitals with alpha electrons. And then after all those orbitals are filled with one alpha electron, and then you add beta electrons. So we have only 2 electrons, therefore we just add 2 alpha electrons in this 5d orbitals. That's rule 1, Hund's rule. Rule 2, now we need to maximize L. How do we maximize L? So what you need to do is you need to maximize the sum of m sub L. So that's why we put this alpha electron in this orbital with the largest m sub L. But do not put a beta electron here because you want to maximize the spin first. The spin is your first priority. So the second electron must be an alpha electron as well, and then we can only put it in here to maximize m sub L. And then we sum up m sub L, 1 plus 2, we got 3, and therefore L can only be 3. And then we look at the spin. 1/2, 1/2, together we have S equals 1 and L equals 3. And J equals from L minus S to L plus S. And then therefore J can only be 2, 3, and 4. So you use 3 minus 1 all the way to 3 plus 1. If S is greater than L, and then you have J equals just S minus L. Again, this is the absolute value of the difference between L and S. For electron configurations that are less than half filled, the lowest energy level has the smallest J value. You have 3 different J values. So therefore, we add this J value equals 2 in the subscript here. 3F2 is the lowest energy level, 3F is the lowest energy atomic term or ground state atomic term. So again, if you have S equals 1, then 2s plus 1 equals 3, so you put a 3 here. That's the spin multiplicity. Also, it corresponds to the number of possible values of m sub s. Again, m sub s may adopt 3 different values, from -1, 0 to +1. And how about this f? Again, you look at the value of L. L equals 3. When L equals 3, you look it up. 0, 1, 2, 3. Therefore, you have 3f here. Again, in this situation, this 5d orbitals are less than half filled. Therefore, you use the smallest j value 2 here. The lowest energy level is 3f2. Now, d3, the ground term is 4f. Again, you want to maximize the spin. So how do you maximize the spin? You need to maximize the sum of m sub s. Therefore, we have 3 alpha electrons here, and then the maximum number for the sum of m sub s is 3/2, and then s equals 3/2. How about L? Again, we put the 3 alpha electrons in a way to maximize the sum of m sub L, and we get 3 here. Therefore, L equals 3. How about J? J can be from the difference between L and S to the sum of L and S. Therefore, J may adopt 4 different values here. Again, the lowest energy level is just 4f 3/2. 4 is the spin multiplicity because m sub L may adopt 4 different values from -3/2, -1/2, +1/2, and +3/2. F, again, L equals 3, so you just look it up, SPDF, and then you have this F here. J value should be the smallest one because, again, in this situation, the 5d orbitals are less than half filled. How about D4 ground term? It's 5d. Again, we need to maximize m sub s. We need to maximize the sum of m sub s in order to get the ground state atomic term. And when you do that, you have 4 alpha electrons, therefore s equals 2, because the maximum value of the sum of these 4 electrons is 2, and then s equals 2. How about L? Again, you sum it up. This 4 numbers, you get 2, therefore L equals 2. So J must be from L minus S, that's 0, all the way to L plus S equals 4. And again, 2s plus 1 equals 5, therefore we'll put 5 here. And the symbol for the orbit angular momentum is d because L equals 2. So how about J? J value has to be 0. Now exactly how filled here. So D5 ground term. Now to maximize this the sum of the m sub s value, we have 5 alpha electrons, and then s can be 5/2 only, and L must be 0 here because, again, you sum up these 5 numbers, you have the maximum value for the sum of m sub L, which is 0, and then L can only be 0, and then J has only one possible value, which is 5/2 because L is 0. And then in this case, there's only one possible J value, and therefore the atomic term is 6s. The level is 6s with 5/2 in the subscript to indicate the J value here. Now, in general, if we have more than half-filled electron configurations, for example, we have D6. The atomic terms of D6 is exactly the same as D4. D7 is the same as D3. So how about p orbitals? P5 is exactly the same as P1. P4 is exactly the same as P2. How about f orbitals? Same thing. If you have F10, it's just F4. So they, for example, this in general, this F14 minus n is exactly the same as Fn regarding the atomic terms. But if you're talking about the levels, you have to worry about the J values. And again, if it's less than half filled, J value should adopt the minimum value. If it's more than half filled, you must have the maximum value of J. So why is that? Again, it's just because the S number and the L number correspond to the spin angular momentum and the orbit angular momentum. And the J is the coupling between the magnetic moment generated by the spin and the orbit motion. All right, let's look at D6. So D6 is exactly same as D4 regarding the atomic terms. And also we can do this analysis. We fill up this 5 d orbitals with alpha electrons, but then there's a 6 electron. It has to be beta, and then we look at the sum of the m sub s, which is just 2. Because this one alpha and this one beta cancel. And also we try to maximize the value of m sub L. We get -2, -1, 0, 1, 2, and 2. So the sum is 2. So we have S equals 2, L equals 2. And what about J? J equals from L minus S, that's 0, all the way to L plus S, that's 4. And therefore the ground term is 5D, the same as D4 electron configuration. But over here, pay attention here. Now you need to use the largest value of J, which is 4 in the subscript. How about D7? D7 is the same as D3. You get atomic term of F4. I'll let you verify this by looking at this table. And then you need to use the largest value for J. So J can be as large as L plus S, which is 9/2 here. And remember, when you have J equals 9/2, the value of M sub J can adopt 2J plus 1 different values. In this case, 2J plus 1 equals 10, so you have 10 different values. The reason is M sub J is the Z component of J, and it can be from -J all the way to +J. So there are 10 different values here. And once you have the values of L here, L, S, J, and M sub J. Okay, for example, you say M sub J equals -9/2 or +1/2, and then you have a state. And then you have state. And all these 10 different states have the same energy unless you place this atom in an external magnetic field, and then you will see energy splitting here between these 10 different states.